Hi, this is in my continuing series that I'm calling Video Boosts to kind of support our classroom activity. You can probably hear the cars racing by my house. What I want to do in this one is remind you of a reaction that you must learn, and I think we did it very quickly in class, and I think people are going to forget about it. And that is the addition of KMnO4 in water or the addition of osmium tetroxide with sodium bisulfite in water. Both of these reactions achieve the same goal. I want you to really kind of memorize them as synthetic tools. The value of these reactions is that they are complementary to epoxide opening in making what are called vicinal diols. Okay? If you have an epoxide and you add OH minus to it with some water, you will make what is called a transvicinal diol. Our system's falling here a little bit. Okay, but so again, the way you would make a transvicinal diol is from an epoxide opening with either sodium hydroxide and water or hydronium ion, water, okay? But the synthetic complement to this reaction is the use of potassium permanganate in water, which is an oxidation. This is also. Or osmium tetroxide with sodium bisulfite, I apologize, in water, okay? Also an oxidation. How do you know it's an oxidation? Lots of oxygens around a metal, okay? These are made from alkenes, okay? And if you had either of these reagents, if you had KMnO4 in water, you will obtain the vicinal diol that is cis. And we went over this in class. And we did a little bit of the mechanism in class, though I will not hold you responsible. This can also be accomplished using osmium tetroxide and sodium bisulfate or hydrogen sulfite in water. Okay? These reactions, again, complement the epoxidation reaction, and because we did it quickly, I'm a little worried that it'll get lost in the shuffle. All right, the last thing I wanted to do tonight is another problem considering kinetic versus thermodynamic control in the addition. How are we for time?
4 minutes.
Okay. To conjugated alkenes. They're really polyalkenes, okay? Now, we did this very simple version of 1,2 versus 1,4, so I'm going to do one that's a little more complicated, okay? Not uber complicated, but a little more complicated. So supposing you had this was actually on one of the flashcards. Supposing you have this, and you're adding, and don't be afraid to do this, you're adding HCl. Okay, so say we had HCl at, say, minus 78 degrees. What you're going to assume is if you're at minus 78 degrees, that these are kinetic conditions. Okay? How do you do this? At this point, it should be almost organic, no pun intended. And what I mean by that is, if you are learning or starting to understand the roots of what we're doing and seeing the patterns in what we're doing, you start to be able to do it without a lot of memorizing. Okay? Not everything, but a lot of things. And you start to see recurring themes. This is just an addition to a double bond. Okay? So what you do is you're going to take the hydrogen and add the hydrogen to the less substituted side according to the Markovnikov addition, such that you will obtain the more stable carbocation. This is the first reaction you ever learned, okay, in this course. When you do this, and for those of you who are not into the mechanism, I urge you to start practicing this. We know this reaction produces carbocations. Frequently, the carbocations rearrange, okay? But in this case, we don't get rearrangements because we are in a resonance situation. This is an allylic cation. Okay, what do we know about allylic cations? They have resonance stabilization, okay? So, what would the other resonance form look like? And for those of you who draw hybrid structures, you might want to draw everything out in this case because you might have a little trouble getting the products, okay? That's the other resonance form. What did I do? You could do the 1, 2, 3 dance. 1, 2, 3 dance, where you put the double bond between 1 and 2 and the new charge at 3, or if you're an arrow pusher, you just take this electron pair and move it in. But this cation forms immediately. Immediately you have both of these charge sites. So what should happen organically, right? Cl- should either attack here or Cl- should attack here. What does this lead to? Do we have a good picture of that? Mm-hmm. What should this lead to? Okay, what are our products? This should lead to this product. Okay, that's the so-called 1,2 product. It's only called 1,2 because the H went into 1 and the chloride went into 2. And then the other product, because of the resonance, would look like this. The H would be here, the double bond here, and the chlorine here. This is the so-called 1,4. They're not always 1,2 and 1,4 products. But the thing we know is that this product is the kinetic product. The kinetic product is the product that forms fastest. And we talked in class about why this product forms fastest. When that H bonds up, that chloride just jumps right onto the charge as it's forming. In other words, as we said in class, it's a proximity issue. The chloride is just closer to that charge, so it grabs it faster. So this one forms fastest when you're under very low energy conditions, as is minus 78 degrees. So this is our minus 78 degrees. A convenient temperature for organic chemists because it's the temperature of dry ice and acetone. When you're under very low energy temperatures, what happens is what has the lowest energy barrier because there's not enough energy to get over high barriers. Okay? This guy, this 1,4, is the thermodynamic product. And remember, I'm almost out of time?
9 minutes.
Okay. Is the thermodynamic product. This would form at elevated temperatures. Okay, why is it the thermodynamic product? Do we look at the cation? No. Don't look at the cation. Look at the double bond for its conjugation, which we don't have any here, and look at the double bond for its substitution. In this case, this double bond is tri-substituted. In this case, this double bond is tetra-substituted. And we know from empirical data, from combustion data and heats of hydrogenation, that tetra-substituted double bonds are more stable than tri. This product should form under high energy conditions. In other words, This product should be the deep energy well. Remember we talked about walking around in the field and falling into the holes? This is the deep hole that you can't get out of, okay? So that's all for tonight. Thanks. See you in class.